Hello everyone, welcome back to VLSI Careercraft. I am Mounika Kelam, and today we'll be kicking off a brand new series, The Real World Chip Design Journey. In this series, we'll be diving into the complete life cycle of a silicon chip, and we answer fundamental question every VLSI engineer needs to know. That is, how billions of transistors go from paper specification to final shipped product at industries like Intel, NVIDIA, Qualcomm, Apple, AMD, etc. So think about it. Every GPU powering ChatGPT, every chip inside your iPhone, and every processor in the data center start with a blank document which contain the specifications of what the chip actually needs to do. So it takes 200 to 300 engineers, 3 to 4 years, and hundred millions of dollars to put this technology into your hands. This series is about looking at the big picture, not the job of a single team. So in part one today, we will discuss why understanding this end-to-end flow is so critical, and we also analyze high-profile case studies from Intel, Apple, AMD, and NVIDIA to see what actually happens and how much it costs when hardware bugs escape to final silicon. So let's get started. You might just wonder, hey, I am an RTL engineer and why do I care about physical design engineer's job or SDA engineer's job? But remember that the code written by an RTL engineer will be touched by 10 other teams before it goes to production. According to semiconductor industry's rule of thumb, a bug found during design review can cost hundreds of dollars, but exact same bug found after silicon can cost $10 million and 6 months of product schedule. This is why avoiding costly mistakes and collaboration across the team become important. Also note that engineer who understands the full flow and not just their part of work can become leads, architects and managers faster. Also, every phase has unique risks like schedule slips, silicon bugs and yield failures. So these can be mitigated when you know them early. This is where understanding the complete flow helps to manage risks. So let's time travel back to 1994 and look at one of the most infamous hardware disasters in tech history, the Intel Pentium FDIV bug. Imagine you are Intel and you just shipped the Pentium processor, the absolute cutting edge technology at that time. Everything is going great until a college maths professor named Thomas Nisley noticed something terrifying. The most advanced chip in the world literally cannot do math correctly. For certain specific calculation, the floating point division unit was spitting out the wrong answers. So what is the root cause? A tiny microscopic error in handful of entries within the hardware lookup table. At, at first, Intel tried to brush it under the rug. They told the public, don't worry, this will affect only highly sophisticated users. But they underestimated the power of early internet. The story went completely viral. The backlash was so intense that IBM actually halted all the shipments of Pentium-based PCs. Finally, Intel CEO Andy Grove has issued a humiliating public apology and agreed to replace every single flawed processor. The total cost of the tiny lookup table error is $475 million. So why I'm telling you about this? As a students and future engineers, this is most important lesson you can learn today. This is why design verification engineers exist. When your manager or professor asks for 100% coverage, they are not just giving you the busy work. In silicon industry, missing even 0.1% of your coverage can lead to catastrophic unpatchable product failure. Let's fast forward to much more recent example in 2021. Apple has just released the M1 chip. The tech world was completely blown away by its speed and battery life. It was considered a masterpiece of engineering. But then a security researcher named Hector Martin started poking around and found a crack in the armor. He discovered a hardware vulnerability baked right into the physical silicon of the chip. The flaw was hidden deep within something called memory consistency model. Now, if you haven't taken advanced computer architecture yet, think of memory consistency like a shared Google document. If multiple programs are programs are editing the same document at the same time, the chip needs strict rules to make sure everyone sees the most updated version. But under very specific conditions, the M1 chip broke those rules. It allows data to leak between different programs, completely shattering the security walls that the operating system relies on. This was a massive deal. It was so serious it earned CVE, which stands for Common Vulnerabilities and Exposures. In cyber world, getting a CVE means your bug is official and globally recognized as security threat. But here is the jaw-dropping part. Apple could not fully fix it. When you have a bug in an app, the developer just pushes a software update over Wi-Fi. But hardware bug in memory subsystems means the physical wires, logic gates printed on the silicon are flawed. You cannot download a physical wire. So Apple had to essentially admit it. This is a hardware issue and it cannot be corrected in software. Now the M1 is still a phenomenal chip. Apple found ways to manage the risk. But what I want you to really think about, Apple has some of the best high-paid silicon engineers on the planet. Yet, the bug slipped past simulation, where they tested chip in software. It slipped past emulation, where they tested it on chained supercomputers. It survived all of that and shipped inside millions of MacBooks before anyone caught it. So, what is the lesson for you? Is in the software you get second chances. In hardware, once you reach tape out, the final step where your design is sent to the factory to be printed on physical silicon, there is no going back. So when you are verifying memory, cache controllers, security paths, you cannot just run few tests and hope for the best. This is why exactly we use formal verification, a process where engineers use complex mathematics to literally prove that bug cannot exist. Because in VLSI industry, a bug that slips to silicon is permanent. Now let's look at the completely different kind of hardware issue. This one isn't about chip crashing or leaking secure data. This is about what actually happens when chip breaks its promise. The year was 2019 and AMD just launched Ryzen 3000 series and the hype was off the charts. AMD advertised that the chip would run at very high speed of 4.6 GHz. But the moment tech reviewers and gamers got it in their hands, they noticed a massive problem. The CPUs were consistently falling short. They were not hitting 4.6 GHz target. To be clear, the chips were not functionally broken. They computed math perfectly. They ran games fine, but they did not do what the specification sheet said they would do. So what is the root cause here? It wasn't actually a flaw in physical silicon. The silicon itself is totally capable of hitting 4.6 GHz. The problem was in the power management firmware and precision boost algorithm. If you aren't familiar with modern processors, they don't run at one speed. They have algorithms that constantly monitors the temperature and workload to decide how fast the clock frequency can go. Think of a silicon as high performance sports car engine and the power management firmware as electronic speed limiter. The engine was completely capable of going 200 miles per hour, but the speed limiter got overly conservative, panicked about the engine getting too hot, and slammed on the brakes too early. So AMD eventually pushed BIOS update to fix the overly conservative algorithm, but the damage to their PR was already done. The Ryzen 3000 launch became one of the most controversial topics of the year simply because the real world performance didn't match the published targets. So what is the lesson here? In VLSI industry, we have a holy trinity called PPA, power, performance, and area. These aren't just arbitrary goals, they are binding contracts with the customers. During architecture phase, the architect set the target for maximum frequency. Once the target is set, every single downstream team, RTL designers, verification engineers, physical design engineers, sweats their blood to meet the target. They optimize every single wire, every single logic gate to make sure chip can hit 4.6 GHz. But as AMD learned, If your system level power management makes the wrong assumptions about real world workloads, all of the hardware goes out of window and you ship a chip that underperforms. This is why exactly performance modeling is at very beginning of the architecture phase and is absolutely mandatory. You cannot just design a fast chip, you have to mathematically model how it will behave in real world before you even print it on silicon. For our final case study, let's look at a scenario that is completely different from others. What happens when a chip has absolutely zero bugs, works exactly as it was designed to, and yet still it results in a massive class action lawsuit? In 2014, NVIDIA launched GTX 970 graphics card. They proudly advertised it as having 4 GB of high-speed memory. It was an absolute smash hit and gamers loved it because it offered incredible performance for great price. But in early 2015, users started noticing something weird. When a heavy or demanding game tried to use very last 512 megabytes of that 4 gigabytes memory pool, the game would start lagging and stuttering. That final chunk of memory was running significantly lower than the rest. So what was the root cause? Was it a bug? No. It was deliberate choice made during the very first step of chip design process, that is architecture phase. To save money and efficiently reuse existing silicon chip for a cheaper graphics card, the architects decided to split the memory. If you think of memory bus like a highway that transports data, the architects gave the first 3.5 GB a massive multi-lane superhighway to move data at blazing speeds. But for the last 512 megabytes of memory, they routed it through a narrow one-lane road. The chip wasn't broken. It was doing exactly what the blueprint said it should do. The RTL engineers coded it perfectly. The verification team verified it perfectly. But the marketing team sold it to the public as 4 GB of equal high-speed memory. When gamers found out that the last half gigabyte was actually slow, they sued NVIDIA. The company has to settle the lawsuit for 30 million and issue refunds to their customers. So what's the lesson here? In VLSI industry, architecture decisions are practically legal documents. When you become a computer architect, your job is not just to design a clever way of saving money. You are responsible for the reality of the chip. In this case, every single downstream engineer team did their jobs perfectly. The failure was the architecture specification wasn't clearly communicated to people while selling the product. As an architect, you don't just own what chip does. You are responsible for making sure everyone understands exactly how it does. But a misunderstood spec can easily turn it into a multi-million dollar legal disaster. And with that, we are officially done with part one. We have seen how tiny bugs can cost hundred millions of dollars and why understanding big picture makes you incredibly valuable engineer. Thank you for spending time with me today. Don't forget to hit subscribe button to join VLSI Careercraft community and also come follow us on LinkedIn to keep conversation going. Thank you.